Have you ever watched, say, a rocket launch? Just feeling that incredible power.
Yeah, it's a
Or even
mess.
something quieter like how a jellyfish moves so gracefully in the water.
Those almost invisible forces.
Exactly. They're not just cool to watch, they're these dynamic interactions the kind engineers are always trying to figure out, predicts.
Especially with fluids involved.
Right.
Water, air, rocket fuel.
Right. We're talking forces, motion,
Yeah.
how it all connects. And today, that's our focus. We're doing a deep dive into something called momentum analysis of flow systems. And we're drawing from a pretty solid engineering textbook here, the kind that really lays out the basic principles.
Yeah, and our mission really is to slice through some of that complex math and the jargon.
Get to the good stuff.
Exactly. We want to give you a shortcut, those essential sort of nuggets of knowledge about forces and motion in fluids.
So by the end, you'll have a really good handle on this core engineering idea.
Mm-hmm.
See it working everywhere.
Yeah.
Okay, so if you're an engineer facing these complex fluid problems all the time, you need answers, right? You can't just guess.
And you don't have unlimited time or budget, usually.
So what's the toolkit look like? How do you get reliable answers without, spending months on it?
That's the million-dollar question. So our source points to 3 basic ways to analyze fluid flow. First up, you've got the differential approach.
Right.
Think of it like using a super powerful microscope on the flow, breaking it down to tiny, tiny pieces.
Sounds detailed.
Oh, it's incredibly precise. But the downside is it's usually really complex. Needs a lot of computer muscle, a lot of time.
Right. What else?
Then there's the experimental approach, actually building a model or setting up a test rig.
Seeing it happen for real.
Exactly. So highly accurate data, usually. But again, it can be really time-consuming, expensive to set up and run.
Okay, so precise but slow, or accurate but maybe costly. Is there a middle ground?
Yes. This brings us to the third way, and honestly, for a lot of engineers, this is the go-to, the control volume approach.
Okay, this sounds important.
It really is, because here's the thing. This method is surprisingly fast and relatively simple.
Faster. Simple, but does it work?
Yeah, it gives answers that are, well, accurate enough for a huge range of engineering tasks, even with its simplifications, just doing this analysis, maybe even just on paper. It's always been, as the book says, an indispensable tool.
An indispensable tool. Okay, so that's the engineer's shortcut then.
In a way, yes. It lets you figure out the big picture forces and torques from the fluid flow.
Without getting totally lost in every little swirl and eddy inside the system.
Precisely. It's about efficiency, getting a good solid answer quickly.
Can you give an example? Make it a bit more concrete.
Sure. The source has a great one, actually. Think about the jellyfish, Aurelia aurita.
Okay, the jellyfish.
They put some fluorescent dye in the water just upstream. As the jellyfish relaxes its bell shape, it actually pulls that dyed water underneath. Then when it contracts, it pushes that fluid out and it forms these amazing vortex rings underneath it, little swirling donuts of water.
Vortex rings, okay.
And these rings, they do 2 things at once. They help with feeding, drawing stuff in, and they provide propulsion.
Wow. So it's pushing itself forward by pushing water backward in these neat little rings.
Exactly. It's manipulating the momentum of the water around it. A beautiful, living example of momentum analysis in action.
That's fascinating. So whether it's a jellyfish or a giant rocket, it all comes back to some basic physics, right? Newton's laws.
Absolutely. That's the bedrock.
Okay, quick review then. Newton's first law. That's inertia, right?
Yep. Body at rest stays at rest. Body in motion keeps going at the same speed and direction unless some force acts on it.
Simple enough. Then the second law, EFMA.
Usually, yeah. Force equals mass times acceleration. But, and this is a key insight for fluids, it's often way more useful to think of it differently.
How so?
As the rate of change of momentum of a body equals the net force acting on it.
Rate of change of momentum. So mass times velocity, how that changes over time.
Exactly. Momentum is mass times velocity. So how fast that product is changing, that's equal to the force.
Why is that phrasing better for fluids than just EFMA?
Good question. Because with fluids, we're often dealing with continuous streams of stuff. Mass is flowing in and out of whatever we're looking at.
Right. It's not usually a single solid object.
Precisely. And the velocity is changing as it flows through. So thinking about the rate of change in momentum directly helps us calculate the forces generated by speeding up, slowing down, or redirecting that flow. That's why we often call it the linear momentum equation in fluid mechanics.
Okay, that makes sense. It handles the flow aspect better.
It does, and it leads straight to conservation of momentum if there's no net external force on your system.
The total momentum stays the same. It might move around, but the total amount is constant.
You got it. And then there's Newton's third law.
Action-reaction. Push on something, it pushes back equally hard.
Yep.
For every action, an equal and opposite reaction. Crucial for things like rocket thrust or the force on a pipe bend.
Okay, so linear momentum is sorted. What about things that spin?
Right, that's angular momentum. It's the rotational version.
Okay.
So the angular momentum equation says the rate of change of angular momentum is equal to the net torque acting on the body. Torque is like the rotational version of force.
So instead of ethma, it's like torque I times alpha. Moment of inertia times angular acceleration.
That's the simple form for rigid bodies, yes. M equals Ia. More generally, it's the rate of change, dH dt, where h is angular momentum.
And there's a conservation principle here, too.
Absolutely. The conservation of angular momentum. If the net external torque is 0, the total angular momentum stays constant. This is often written as I times omega, angular velocity, equals constant.
I times omega is constant. That's the ice skater thing, isn't it?
Exactly. Ice skaters spinning faster when they burn their arms close to their bodies.
Because their moment of inertia, gets smaller. Right. Mass is closer to the axis of rotation. So to keep I times omega constant, omega, the spin speed, has to go up.
And divers doing the same thing, curling up midair.
Same principle. Divers rotating faster when they curl after the jump. Reduce I, increase omega. It's conservation in action. Looks like magic, but it's physics.
It really is neat. Okay, so we have these powerful laws, linear and angular momentum. How do engineers actually use them? You mentioned the control volume approach earlier. What exactly is that?
Right. The control volume, or CV, is really the heart of this technique. It's defined as just any arbitrary region in space through which fluid flows.
Any region, so I just draw a box.
Pretty much. An imaginary boundary called the control surface. And the key thing is that this boundary needs to be well-defined. It can be fixed in space, it could be moving, it could even change shape or deform during the process.
Okay, so it's flexible. Examples?
Sure. A fixed one might be drawing your box around a nozzle on a fire hose bolted to a tripod. You want to find the force on the tripod.
Makes sense. The box stays put.
A moving one. Think about a jet engine on an airplane cruising at constant speed. You'd probably draw your control volume around the engine, and that whole box is moving along with the plane.
Okay, so the box travels with the objects.
Yep. And a deforming one. Imagine the cylinder in a car engine as the piston moves up and down, pushing exhaust out. The space you're analyzing between the piston head and the cylinder head is changing shape.
So the box itself squishes and expands.
Exactly. And in those moving or deforming cases, you have to be careful with velocities.
How so?
You need to use the relative velocity, that's the fluid velocity, relative to the control surface itself. We call it VR, and it's V minus VCS, the velocity of the control surface.
Because the fluid crossing the boundary depends on how fast the boundary itself is moving.
Precisely. It's crucial for getting the mass flow rate right when your box isn't stationary.
Okay, so drawing this box, this control volume,
Yeah.
You said it's an art. What makes a wise choice?
It's about simplifying the problem. You need to think about the forces acting. There are body forces like gravity acting on everything inside the volume.
Like the weight of the fluid.
Right? And then surface forces acting on the boundary, the control surface. These are things like pressure pushing on it, viscous forces like friction from the fluid rubbing against a surface, and reaction forces where the boundary cuts through solids.
Okay, so how does that help you choose?
The key idea is draw your control volume boundary strategically so that the forces you don't want to calculate stay internal to the volume.
Hide the complexity inside the box.
Essentially, yes. You want the boundary, the control surface, to cut through places where you do know the forces, like atmospheric pressure, or where you want to find the forces, like reaction forces.
You mentioned pressure. Is there a trick there?
Yes. A very common simplification. We usually work with gauge pressures. That means we subtract atmospheric pressure everywhere.
Why do that?
Because atmospheric pressure acts pretty much equally on all sides of your control volume, right? So its net effect often cancels out. Working with gauge pressure just cleans up the math, lets you focus on the pressure differences that actually drive the flow or cause net forces.
Okay, smart. Let's take that faucet example from the source. Water flowing through a tap with a valve partly closed.
Right. So option 1, control volume A. You draw the boundary just around the water itself, following the inside of the pipe and valve.
What's the problem there?
Well, now your control surface is touching the pipe walls, the valve surfaces. You'd have to figure out all the complicated, varying pressure forces and friction forces all along those surfaces. It's a mess, a real headache.
Okay, not ideal. What's option 2?
Control volume B. This time, you draw a bigger box. The boundary slices through the solid pipe walls upstream and downstream, and maybe even slices through the bolts holding the faucet to the sink flange.
So the complex internal shapes are now inside the box.
Exactly. Now, the forces acting on your control surface are much simpler. You've got the pressure forces where the water enters and leaves, the weight of the faucet and water inside, and importantly,
The reaction forces where you cut through the bolts.
precisely,
Yeah.
the net reaction force acting at the portions of the control surface that slice through the flange bolts. That's probably what you wanted to find anyway, how much force the bolts need to provide.
Wow. So choosing where you draw that line makes a huge difference. It's not just about the math, it's about framing the problem cleverly first.
That's it. It's often the most critical step, knowing where to focus your attention.
Okay, so we've got the concepts, the laws, and the smart way to set up the problem with control volumes. Now let's get into the actual math a bit. How do engineers calculate these forces and torques?
All right. The workhorse equation is the linear momentum equation for a control volume.
Where does that come from?
It comes from something called the Reynolds transport theorem, which sounds scary, but it's basically a clever mathematical bridge. It lets us take a fundamental law that applies to a fixed chunk of mass, like Newton's second law,
Right.
and apply it instead to a region in space, our control volume that fluid is flowing through.
Okay, so it translates the law for the control volume world. What does the equation actually say?
In essence, it links the total sum of all the external forces acting on the control volume
Gravity, pressure, reaction forces.
to two things happening with momentum. First, the rate at which the total linear momentum inside the control volume is changing over time.
So if stuff inside is speeding up or slowing down.
Exactly. Plus the net rate at which linear momentum is flowing out of the control volume across the control surface, carried by the mass flow.
Okay, so forces equal change inside plus net flow out.
That's the gist. It's an accounting principle for momentum.
Are there simpler versions?
Yeah.
Like common cases?
Oh, definitely. The most common is steady flow, if the flow conditions aren't changing with time.
Like that faucet example, once it's running smoothly.
Right. Then that first term, the time rate of change of momentum inside, just goes to zero. The equation gets much simpler. Forces just balance the momentum flow rate in and out.
Nice. What else?
Another really interesting detail is something called the momentum flux correction factor, usually called beta.
Beta. Why do we need a correction factor? Isn't momentum just mass flow rate times velocity?
Well, that assumes the velocity is perfectly uniform across the inlet or outlet area.
Which it probably isn't in real life, right? Flow is faster in the middle of a pipe, slower near the walls.
Exactly. Beta accounts for that non-uniform velocity profile. It corrects the momentum flow rate calculation.
Is it a big correction?
It can be. For smooth, slow, laminar flow in a pipe, beta is actually 43. That's a 33% correction. Ignoring it would cause significant error.
Wow, okay.
For more common, messy, turbulent flow, beta is usually much closer to maybe 1.01 to 1.04, so the correction is smaller.
Less critical, but still there.
Right. The source says it's still wise to keep it in our equations, partly for accuracy, but also just to remind ourselves that profiles aren't always uniform, especially if we ever encounter laminar flow. It's a neat reminder of real-world effects.
Good point. Any other special cases for linear momentum?
Well, there's the situation where you have no external forces, or maybe the forces are negligible compared to the momentum change.
Like a rocket in deep space.
Perfect example. This is where we get the concept of thrust. The rocket throws mass exhaust gas out the back at high speed. That creates a huge change in momentum flow rate, leaving the control volume, the rocket.
And by the equation, that momentum change must be balanced by a force.
Which is the thrust pushing the rocket forward. The source mentions a spacecraft, 12,000 kilograms, slowing down by firing gas out at 3,000 meters. Even if the mass flow rate is relatively small, say 80 kilograms, that produces a massive 240 kilonewtons of thrust. That's huge.
It really shows the power of changing momentum at high velocity. Okay, let's make this even more concrete with some of those textbook examples.
Sounds good. Example 6.2 talks about a deflector elbow in a pipe. Water's flowing horizontally. Then the pipe bends upwards 30 degrees.
Okay.
Using the linear momentum equation, you can calculate the forces horizontal and vertical needed in the anchor bolts to hold that elbow in place against the push of the water changing direction.
So practical design stuff.
Very much so. Then example 6.3 looks at a reversing elbow, like a 180-degree U-bend.
Turning the water completely around.
Right. And guess what? The force required to hold that in place is much, much larger than for the 30-degree bend. Makes sense, you're reversing the momentum completely, needs much stronger connectors.
Yeah, you can feel that intuitively. What else?
Example 6.4. A water jet striking a plate. Think of firing a jet of water straight at a flat board. The equation tells you the force needed to hold that board stationary.
Like the downwash from a helicopter hitting the ground.
Similar idea, yes, calculating that force. And example 6.5 is a wind turbine.
Ah, relevant.
Yeah, a 30-foot diameter turbine. In a 7 millillar wind, it might generate, say, 0.4 kilowatts of power. The momentum analysis also tells you the horizontal force the wind exerts on the mast, supporting it, maybe 31 pounds force.
Okay. But what happens if the wind picks up?
This is where it gets interesting. What if the wind doubles to 14 millillar?
Force doubles, power doubles.
Not quite. Power depends on the cube of velocity. So doubling the wind speed increases potential power by 2 cubed, which is 8 times. So 3.2 kilowatts.
Wow, 8 times the power.
And the force on the mast, that goes up with velocity squared. So 2 squared is 4 times the force. About 126 pounds force now.
So the loads increase much faster than the wind speed. Understanding that non-linear relationship is crucial.
Absolutely critical for designing turbines that are both efficient and strong enough.
Okay, fantastic examples for linear momentum. Let's switch gears to rotation. We talked about the concept, now the equation for angular momentum.
Right, the angular momentum equation for a control volume. It's the rotational equivalent of the linear one.
So analogous structure.
Very similar. It says that the sum of all external moments, torques, acting on the control volume,
equals the time rate of change of angular momentum inside the CV.
plus the net flow rate of angular momentum out across the control surface by mass flow.
Same pattern. External cause, torque, equals change inside plus net flow out, just with rotational quantities.
You've got it, accounting for spin.
And I bet this has some cool applications too.
Definitely. Example 6 to 8 looks at the bending moment on a water pipe. Imagine an L-shaped pipe sticking up from the ground with water flowing through it entering the corner.
Okay.
The flowing water, and even the weight of the pipe and water, creates a twisting force, a moment, at the base where it connects to the ground. The angular momentum equation helps you calculate that moment to make sure the support is strong enough.
Prevents it from snapping off at the base.
Exactly. And example 6.9 is really neat. Power generation from a sprinkler.
Like a lawn sprinkler. You can get power from that.
Well, imagine modifying one. 4 arms, water comes in the center, flows out the nozzles tangentially. As the water sheets out, Newton's third law means there's a reaction force, a torque, making the sprinkler spin.
Okay, yeah, standard sprinkler action.
But now, connect that spinning shaft to a small generator. The source example has water flowing in at 20 liters per second, and the sprinkler turbine spins at 300 RPM.
And it generates power.
Yep. It calculates to about 16.9 kilowatts in this specific setup. The angular momentum change of the water flowing out is directly related to the torque produced.
That's surprisingly high. Almost 17 kilowatts.
It depends on the flow rate and speed, of course. But here's the interesting part. What if the sprinkler gets stuck? Say the shaft locks up, RPM is 0.
No spinning, no power.
Right.
Yeah.
Power is torque times angular velocity. If velocity is 0, power is 0. But the torque would actually be at its maximum. The water is still trying to make it spin.
Max torque, 0 power. What about the other extreme?
If you disconnect the generator entirely so there's no resisting load.
It would just spin faster and faster?
Up to a point. It would accelerate until it reaches its runaway speed, in this example, about 1013 RPM. At that speed, the resisting torque from friction and such balances the driving torque from the water jets. The net torque becomes 0.
And if net torque is 0?
Power generation is also 0 again. Fascinating trade-offs between torque, speed, and power output.
That really illustrates the angular momentum balance.
Yeah.
Okay, wow. We've covered a lot of ground here.
We have, from Newton's basic laws all the way to practical engineering calculations.
We've unpacked momentum analysis, linear and angular, saw how crucial that control volume choice is.
Yeah, that setup is key. Framing the problem right.
And even dug into details like that beta factor, showing how real-world imperfections matter.
Little details can sometimes make a big difference, especially in laminar flow, as we saw. It's about knowing when those details count.
It really gives you a powerful lens to understand things. From the subtle way a jellyfish creates vortices to swim.
To the massive forces involved in wind energy generation, it connects the small and the large.
So thinking about this for you listening, what's the takeaway?
Well, next time you see something like a fire hose blasting water, or you feel the wind pushing against a large sign, or even just watch an ice skater pull in their arms.
Think about the momentum.
Exactly. Consider those invisible forces, the transfer of linear or angular momentum that's happening. These principles aren't just in textbooks, they are constantly at play all around us.
Which really leads to a final thought, maybe. What other everyday things can you now look at differently through this lens? Where else is momentum shaping the flow of the world around you?
Keep an eye out. You might be surprised how often you see it once you start looking.